Hi everyone, today we're going to be looking at damping. So what do we mean by free and forced oscillations? The effects of damping on an oscillatory system, so how damping can affect anything that's oscillating basically. The observed forced and damped oscillations for a range of systems. What do we mean by resonance and natural frequency? You will also look at amplitude and driving frequency graphs and practical examples of forced oscillations and resonance. Okay, so let's start firstly with what do we mean by free oscillations. Now, free oscillations is where a system is given initially a little budge to give it a bit of displacement, and then it's allowed to freely oscillate. So there's no external forces that are constantly causing it to oscillate at a specific period. Now, the system will continue to oscillate at that set frequency, which we call the natural frequency, F naught. Every single object does that, by the way, including parts of our bodies and including glass. So one example of a free oscillation that you all have experienced probably in your lives is to sit on a swing, right? So if someone pushes you just once, so they give you an initial displacement, they displace your body initially with the swing, the swing will still vibrate freely even after you stop pushing. So with just one push, the swing, including yourselves on the swing, will vibrate at a specific frequency naturally until obviously you stop oscillating. We're going to talk about that in terms of damping in a second, in a bit. So yeah, in free oscillations, you basically give a budge to a system, you move it, you displace it a bit, and then when you let it go, it will just naturally vibrate at its own natural frequency. So that's what a free oscillation is. It's something that you allow to vibrate as natural frequency without any external forces applied. Now, a forced oscillation, on the other hand, is when you do apply a periodic driving force to make the system oscillate. So in this case, you need a driving force that's quite periodic. So you will basically, it will have its own frequency. So you will be pushing, let's say, with 5 newtons on a spring with mass hanging off it every 5 seconds. That's got a frequency. You have a force applied, which is 10 newtons, and you do it every 5 seconds. So that's the period. And if you want to find the frequency, then you do 1 over the period. So in that case, you're providing that constant driving force. You can even connect it to a signal generator, which can cause it to vibrate at a specific frequency. So obviously that driving force will be moving at a certain frequency, and we call this the driving frequency. So we introduce 2 types of oscillations, free and forced, and they both are linked to a specific name of frequency. One of them is natural, the other one is driving frequency. Now, if the driving frequency is equal to the natural frequency of the oscillating object, then the object is gonna resonate. So resonance happens when the driving frequency is equal to the natural frequency, F naught. What do we mean by resonate? Well, when we talk about resonance, we mean that the vibrations of the oscillations will have the highest amplitude as possible. It will have the highest amplitude possible. So it will increase extremely dramatically. And there are some examples we can see this in. Obviously, we're not in class and I don't have any equipment here with me now. But I will show you a diagram about how we can demonstrate it simply. Maybe you can even mimic that at home with whatever you have around you. Before I go to that though, just to stress out something important here. If something resonates and it goes to the highest amplitude that it can, now that can be very dangerous, because if it increases the amplitude so much, it can break the system itself. We will look at it at the end of the lesson a little bit more in detail, but that was the case that happened to a bridge that was blown by the wind. So basically the forced oscillation was the wind. It caused the bridge to vibrate at its own frequency, at its driving frequency, which happened to match the natural frequency of the bridge. Now, obviously, the bridge broke because it was resonating so much. So it was oscillating at such a high amplitude. Remember the amplitude, if this is the bridge connecting two places together, and you have the wind coming at it and causing it to vibrate from side to side, eventually the structure will start crashing down. Remember, you learned that in materials in the in your year 12 lessons. So any motion that continues to amplify this amplitude, so how much it displaces the bridge to different amounts, it will obviously eventually break it. That's actually something that happens with opera singers and glass, the wine glass. So wine glass, if you kind of tap it, or you know, a little bit hard with your thumb or finger, whatever, it will start vibrating, but it's so subtle that you're not going to see it. It actually creates ripples always, and I would really advise you to watch it. Actually, pause the video and watch the how they record in slow motion, how they break wine glass with the sound frequency, and the record in slow motion is quite cool. But anyway, so you will notice that the glass, if you watch that video, you will notice that the glass actually changes shape, starts forming wavy, wavy looking shape at its opening. That means that you're bending the glass, and you know that there's glass is brittle. It's not going to take a lot of stretching to just snap. Now this gets worse and worse the more you match its natural frequency. So if you tapped it, you will cause it to oscillate as natural frequency. However, it's not something that you're driving if you just tap it once. So if it just vibrates at its natural frequency, then that's fine. But if you now intentionally keep matching that with a driving frequency caused by sound waves that match the exact natural frequency of the glass, these vibrations will become so pronounced that the glass will break. Glass is brittle, it can stretch so much. So that's why, even though resonance sounds really cool, it's not quite safe in terms of damage that it can do, including to us. It's not just objects that break. There are parts of our human body that cannot withstand certain frequencies. So one way that you can see it at home or in a lab is if you have like a bit of strong string to use, like a thick string, not a very thin one. You could actually do this at home. So this is Barton's pendulum. You can see resonance in action. What you have is a number of paper cone pendulums of different lengths suspended from a string. Well, they're suspended from a string as well themselves. And you have a heavy pendulum, like you could use metal bob or something, to act as the driver. So what you see here is the driver, the heavier bob, and then all of these are the different lengths of strings with paper cones at their ends hanging. Don't know if you noticed, but one of the strings' length is the same as the bob's length. And there's a reason for that. In the previous lessons, in the first lesson actually, I described how you can do an experiment with a pendulum. And we said that if you change the length of the pendulum, then that's going to affect the period of the pendulum. hence the frequency of the pendulum, since frequency is 1 over t, right? And there's two diagrams now. I'll just explain why. So the driver has a larger weight, a larger mass, so it can basically transfer more energy, because obviously you have a lot of different lengths of objects hanging along the rest of the route. And the pendulums have different lengths of wires they're hanging from. That's because it will mean that each pendulum, if you tap it, it will naturally, just tapping it once only. So let's say I tapped pendulum E, for example, here. Now, if I tap pendulum E, it will start just once, it will start oscillating at its natural frequency, which is specific for a specific length. So since it has this different length from D and C and B and A, it will have a different frequency. So it will oscillate at frequency F, let's call it FE since it's called E. Will have its own frequency, FD, FC, FB, and FA. Now, obviously, this one has a specific length which matches exactly C's one. So this will also oscillate at the same natural frequency as C will, which means this is a driver, and since it has the most weight to cause more energy impact, then it will keep vibrating, it will keep oscillating, and it will oscillate in and out of the page, by the way. Just we're looking at it from the side. Now, E will vibrate, they will all start vibrating. Actually, to be 100% honest, I will suggest that you watch a video of this as well, by the way. It's quite cool to see it in action. So we're going in and out of the screen, basically. We're going in and out. But they will all be going in and out at different rates. However, C will vibrate at the much, since the driver and C have the same frequency, they will start matching each other's frequencies, and the amplitude will start getting bigger and bigger and bigger. And if you looked at it from the top or from the side, like from here or from here, you will be able to see how much cone C and driver are moving compared to A, B, D, or E, for example. So this is witnessing the whole amplitude. Maybe you can do a video to show it if you do this at home. It will be quite cool. Okay, so what's damping now? Now, when you apply an external force on the oscillator, it will reduce its amplitude of oscillation, basically. So damping acts as a way of absorbing that energy of the oscillation and stopping it, basically. Damping. Now, an external force can be anything from air resistance, friction, to suspension in the cars. I will go through some examples. Before I go through that, let's go through what types of damping there are. So it could be light damping. That's when the damping force is small. The amplitude of the oscillation will gradually decrease with time, and the period will remain almost unchanged. Heavy damping is when you have a larger damping force. The amplitude decreases significantly. So I will show you that on the graph as well. Is one of the things that you do need to know. And the period of oscillations increases slightly. So it will affect the period in heavy damping. With very heavy damping, you have no oscillations at all happening, and it will slowly move to equilibrium. So if you displace something, it will slowly move to the equilibrium. It's like those doors in certain buildings in the school or in some shops, where when you push the door wide, it takes a very long time to just come back to close fully, but then it just does it suddenly at the end. That's very heavy damping, basically. So this is how a displacement time graph will look like for the different types of damping. If you have light damping, you can see you have the blue line. The blue line is showing you clearly how you have the amplitude gradually decreasing with time. It shows you also that the force wouldn't be that big, obviously, because you still have the amplitude decreasing with time slowly. And the period is quite unchanged. So from this point to this point is about 1, 2, 3, 4, 5 squares. And from here to here is 1, 2, 3, 4, 5. So yeah, roughly the period remains the same. Now, if you look at, you should be able to reproduce these graphs, by the way, which I think is quite simple and easy because it will make sense to you that obviously the amplitude of something stops. So if I had a pendulum, you would expect the pendulum to eventually stop moving. And that's because air resistance is acting against it. So that's the damping force acting against the oscillation motion. And so the energy basically changes from kinetic to heat energy in most cases. Yeah, so in heavy damping, you can see that the period actually increases. There's the amplitude drops quite dramatically, and yeah, it even stops quite sooner. And then for very heavy damping, you have no oscillation motion at all. It just slowly goes towards the equilibrium position. So that's the displacement at time zero, the way you displaced it. So if you imagine that door, that very heavy door that usually when you push, once you push, it stays open for quite a while. So it will start at the, this is its equilibrium position. So you pushed it, it's there now at time zero. And when you let it go, it slowly comes to a close until it goes to displacement zero again, if the closed door was zero displacement. So these are some examples of resonance. Now, not all of them are bad. I did say it before, not all of them are good, but not all of them are bad either. They are used in watches and clocks. So resonance is used, sorry. Obviously, there's different ways that it works in different objects, in different clocks and watches. There's good people that work around that, actually. And resonance is what keeps them basically working and functioning. Musical instruments function based on resonance. So it's basically resonating the air particles, let's say, between the air column of a musical instrument, or I don't know if I'm correct about this, but something about the violin, those holes next to the violin, they create resonance in those holes, apparently. There's a lot of instruments that use it. I'm not an expert on instruments, though, so any kind of ideas or concepts where it could be used particular in specific instruments, you can let me know, and that would be interesting. And radios, even your satellite dishes at home for TV, they use resonance. So you have the electromagnetic fields are resonating at a specific frequency, that vibrating at a specific frequency. When they meet and when they come to your satellite, they cause those vibrations to be transmitted at the same frequency. That resonance is what creates and transmits signals efficiently. Now, MRI is quite different. I know we haven't done this in the medical imaging, which would have been cool to kind of look at it there, but it's an opportunity to look at it here. In magnetic resonance imaging, they focus on the hydrogen atoms in our bodies. Because our body is so much of water, we have a lot of water molecules, which means a lot of hydrogen molecules. So they rely on the resonance of the hydrogen nuclei of inside the patient's body. So MRIs use something very simple. They use they're huge electromagnets, basically, MRIs. And what they do is they cause the random directions that the hydrogens are aligned with. So if you create a magnetic field and you place that magnetic field by those hydrogen molecules, or in by the person's body, the hydrogen atoms in the body will align themselves with that magnetic field. And when they resist back to their direction, they usually emit waves at a specific frequency too. I won't go too much into the analytics of it, but basically what the hydrogens do, they behave like little magnets themselves. Yeah, and they resonate at a specific frequency, and that's the frequency they emit, and that gets picked up, and it creates an image. But yeah, I won't go too much into it now. I will go through it in the lesson more, actually, because it's a nice topic to discuss a bit more. Now, where resonance actually becomes a nuisance is when it comes to buildings. If there's an earthquake, the buildings are bound to vibrate or oscillate at the frequency that the waves, the earthquake, or the seismic waves are coming at. So what do we do for that? We need to use damping, okay? So when it comes to resonance, the best way to avoid the huge amplitudes and energy taking place at that point in time is to make sure that you damp the system. So damping a forced oscillation will have exactly the same effect as reducing the maximum amplitude at resonance, which is exactly what you want if you don't want people to die from like a broken bridge or anything. This is actually something that was a problem when the Millennium Bridge was built in the UK. It was, for some reason, started taking the vibrations of the people, and it was quite unsteady. And then the more the people were walking, the more they started matching the the vibrations of the bridge from side to side. So they started marching with the same frequency as the bridge was vibrating or oscillating. And they had to close it down, I think, for about 2 years, if I'm not wrong. And from there on, they added they increased the damping systems on the bridge to take away from that forced vibration to take place. So basically, the driving frequency of the people's marching matched the natural frequency of the bridge, which nearly caused it to collapse, which is not something that you want from a bridge. You also don't want that from your car. So this is a simplified version of a car suspension. You have a spring, which is one of the important parts of it. And you also have the second part of the suspension is the damper. Well, sorry, not the damper, the shock absorber. Sorry about that. So the purpose of the shock absorber is so this part, the bronzy looking color, is filled with oil. Now, if the car oscillates at the same natural frequency as the spring's natural frequency, then that will definitely cause the people inside the car to jump to oscillate in essence at the same frequency too. So it will be quite a high amplitude, and that will not be a very pleasant journey. So what they use is the shock absorber that's filled with oil to absorb that extra energy in the vibration, and hence minimize the amplitude. Another example is the Taipei 101 in a building in Taiwan. Sorry. That has a massive damper near the top of the building. It's a very tall building, and it has this very massive damper, which when if there is an earthquake, so the purpose of that is to avoid the destruction of the building. It's quite a tall building, so obviously it needs to be steady. So what they did in Taiwan is actually 510 meters tall, nearly, I think. It was 508. And they placed a very, very heavy pendulum in the suspended from the center of the building, from the top. And they wanted to act as a tuned mass damper. So basically, we reduce the amplitude of the building's oscillations in earthquakes by going against it. That's why very interesting setup they have. So something for those who are interested in architecture or engineering in general. So this is the last thing we'll look at. This is what we said about the amplitude of forced oscillations graph against the driving frequency. Now, let's say we focus only on the zero damping line, which is the red line. You can notice that if I start increasing the object's driving frequency, the amplitude starts increasing as well of the object oscillating. So the amplitude increases as the driving frequency increases. That will lead to a point where it breaks. So that's why you don't see the line continuing. And if it doesn't break, as you keep increasing the driving frequency past the actual natural frequency of the object, it would decrease in the amplitude again. However, for light damping, so the blue line is the light damping, as you increase the driving frequency and you get closer to the natural frequency of the object, and this is by applying light damping, so maybe like air resistance is something that can be considered as light damping. Water resistance is more of a heavy damping, and then oil is usually more of the very heavy damping. So in the case of, let's say, air resistance, if you keep increasing the driving frequency when you get closer to the natural frequency of the object, the amplitude of oscillation increases. But then if you pass up, and there's no breakage, there's no damage done to the object. If you pass that, though, if you keep increasing the driving frequency further away from its natural frequency, the amplitude decreases even more and more with the oscillations. If you go to heavy damping, you see something quite similar, but now the amplitude doesn't get quite that high, and hence you wouldn't have a problem with the building or the car or anything breaking at all. And then you have the very heavy damping, which you nearly see no much difference in the amplitude of oscillation when the driving frequency matches the amplitude, matches the natural frequency. So the amplitude of the force vibration is quite little. Okay, so let's go review our learning objectives. So we have looked at the free and forced oscillations. Remember, this is F naught. This is linked with driving frequency. The effects of damping on the oscillatory system. So we talked about the amplitude of oscillation, which is mostly what it affects. Also the period. And whether it oscillates for a while as well. We also talked about how we can observe forced and damped oscillations for a range of systems. We spoke about resonance. It's when the natural frequency is equal to the driving frequency. We talked about how the amplitude and driving frequency graph for forced oscillations looks. And practical examples, we discussed it throughout it.